Hi, everybody. So our team works on a lot of the problems that Ian and Reed have explained and that you'll be hearing about from the rest of the speakers, in the sense that our goal is at 20,000 meters to help scientists use large-scale parallel computing more effectively, with less focus on the scientific, on the computing plumbing, and more emphasis on their core science. And at like 20 nanometers, what we do is we actually work on issues like how do we place science tasks onto GPUs, and how do we deal with energy management issues in the largest supercomputers. So in between that is sort of this broad spectrum of what we call scientific workflow. And we've created a language called the Swift Parallel Scripting System to make it easier for scientists to do what they always get stuck with on a day-to-day basis. So every scientist across all the domains that you'll run into in the Computation Institute at Argonne and many university centers spend a lot of time running their domain-specific applications on a wide range of computing resources, ranging from like a parallel laptop, with multiple cores, to the largest Cray or Blue Gene systems that we have in our, academic environments. And the challenges of expressing how to run thousands or millions of copies of a scientific program and then feed those results into the next chain in their workflow of analytics and things like that is really daunting. So we've created a language that tries to make all of that easy to do and very clean to express, and it's kind of a very high-level language that allows scientists to really focus on just the flow of their work and leave it to the language's implementation to handle all the mechanics of getting application tasks to diverse computing resources, moving their data, dealing with scheduling, dealing with fault recovery, and dealing with the tracking of what happened in the scientific workflow, so that the scientists and their teams can later, audit, analyze, collaborate, share results, reproduce results, and things like that. So our language makes all of these things possible. And in the process of building this infrastructure, we deal with a fascinating array of both science problems and computer systems level issues, architectural issues, scheduling issues, language issues, programming model issues, and things like that. So it's kind of a fascinating junction of science and computer science that we work in, and there's a lot of opportunity in both of these dimensions for you to get involved, both as students, as users in your domain and discipline, as collaborators helping to build out this infrastructure. So it's used across things like, for example, drug discovery. We have scientists who do molecular docking of proteins and ligands in like millions of combinations, trying to distill out maybe the 5,000 matching drug candidates that look promising, do detailed molecular dynamic studies on those, and take the final 10 to 20 promising chemical compounds to the APS and try to do X-ray crystallography to confirm whether a given drug will help in a computed protein phenomenon. Or we do studies of protein RNA interaction, modeling of doing climate modeling, running climate ensembles, and then taking climate model output and doing the automated analysis of the thousands of files that come out of each modeling room. And like I said, we do this across a broad range of machinery. So we deal with everything from how do we pack scientific tasks efficiently onto an accelerator, a hybrid computing node architecture, all the way to studying how the impact of workflow scheduling on the energy usage in a Cray supercomputer. We run work on Amazon. We run work on all of the campus infrastructures, the Midway main flagship computer in RCC, the Open Science Grid, the National Exceed resource, Blue Waters, Blue Gene, etc. So it's a great place to work on this wide variety of infrastructure. It also brings you in contact with, it sort of joins the Argonne and UChicago communities. So whenever we're walking down the halls here, we're always bumping into either existing users or potential users who need this kind of infrastructure. So if you're a computer scientist who's interested in diverse scientists and science domains, it's a great place to work. If you're a scientist who wants to try to look at productivity techniques, it's also a fascinating opportunity. So I'll leave a stack of cards out here, and we welcome your discussion and a lot of projects, both summer projects, year-long projects to work on. Just give you a brief taste of 3 of the things that we're focusing on now in terms of where we're taking these languages. The first is this concept of using our data flow-based model inside Swift to enhance or to optimize energy consumption all the way down from the node level up to the whole complex, like a room full of machinery that could be using many megawatts of power. Another area that we're looking at is how to marry this programming model that we have, which we call implicitly parallel functional data flow, with mainstream models like Hadoop and MapReduce in general, and try to find the commonalities between those models in integration. And we're looking at issues of how do we take this very productive programming model and extend it from the execution of coarse-grained science applications all the way down to becoming a mainstream on-node programming language that can deal with very fine-grained tasks, going from coordinating the execution of applications that exchange data through files to the completely automated parallelization of functional programs that exchange data through in-memory messages. So we're trying to bring down the granularity of this model, and with it, it's automatic parallelization, it's automated distribution of task and data, it's automated recovery, it's automated analysis. So those are sort of the spectrum of things that we're working on, and we'd love to hear from you, discuss ideas with you, and find interesting projects to engage with you.